Dear students, welcome back to the class. This is our fourth lecture of Control System Engineering. In previous class, we studied about impedance for electrical components, electric network transfer function for complex circuits. The method we used were mesh analysis and nodal analysis. In impedance for electrical component section, we observe that voltage across any component is equal to impedance of that respective component and current flowing through the circuit. Then we started mesh analysis for complex circuits, which was based on certain set of rules. After this, we studied a generalized form for inspection method. Then we studied nodal analysis, which can be applied to any two-node circuit by following given rules. Then we studied a generalized form for inspection method. At last, we studied a three-loop electrical network and analyzed the equation with the help of inspection method. Dear students, till now in this chapter of modeling in frequency domain, we have covered Laplace transform, inverse Laplace, finding transfer function from differential equation, and electrical network components and their circuits. After this lecture, you will be able to find transfer function for various type of electrical networks. And remaining topics will be covered in upcoming lectures. In this lecture, we will study about operational amplifier and their configuration. Basically, we will study two types of configuration. First one is inverting operational amplifiers and second one is non-inverting operational amplifier. After this, we will start translational mechanical system. We will get introduction to the components used under this topic, and we'll try to find transfer function for simple systems. Dear students, now we'll start our operational amplifiers. I will give you a just brief overview of operational amplifiers. Operational amplifier is an electronic amplifier used as a building block to implement transfer function. If you look at the figure of operational amplifier, it specifies that it has two input, V1 of t and V2 of t. Output is V0 of t. A is the gain of the amplifier. V plus and V negative are the actuating voltage of this amplifier. Operational amplifier has few characteristics. It has a differential input which is equal to V2 of t minus V1 of t. It has high input impedance. Ideally, this is equal to infinity. A very low output impedance, ideally which is also equivalent to 0, and a high constant gain of amplification A, which is also equal to infinity in ideal case. The output of operational amplifier is given by gain of the amplifier A and differential input V2 of t minus V1 of t. Dear students, We will study two configurations of operational amplifier. One is inverting operational amplifier and second one is non-inverting operational amplifier. We'll start from inverting operational amplifier. In inverting operational amplifier, one of the input of op-amp is grounded. If you see the figure, the second input V2 of T of operational amplifier is grounded and its output relation is equal to gain of the operational amplifier A with a negative sign multiplied by V1 of T, which implies that in this case our output is out of phase with respect to input. Dear students, now we'll study how to find transfer function for inverting operational amplifier. Now if you look at the figure where input is given by Vi of S, input impedance is represented by Z1 of S and I1 of S is input current. V0 is the output of the system and Z2 of S is impedance of feedback path, where feedback path current is represented by I2 of S. Now we'll use the characteristic which states that op-amp have high input impedance and ideally it is equal to infinity. And we know that current always follow the path which have minimum impedance. So IA of S will be equal to 0, which implies that V1 of S is also equal to 0 as no current is flowing, so there is no potential difference. Now input current I1 of S will be equal to input voltage divided by input impedance. The feedback path current I2 of S will be equal to output voltage divided by impedance of feedback path, which is Z2 of S. Now we will apply nodal analysis at node V1 of S. Now the current entering the nodes are I1 of S and I2 of S, where current leaving the node is IA of S, which is also equal to 0. So I1 of S will be equal to minus I2 of S, and on substituting values of I1 of S and I2 of S, we'll get relation input voltage Vi of S divided by input impedance Z1 of S will be equal to minus output voltage V0 of S divided by feedback path impedance Z2 of S. Now rearranging these variables will give us our desired transfer function, which is V0 of S over Vi of S will be equal to Z2 of S over Z1 of S. In this, Z2 of S is impedance of feedback path, where Z1 of S is impedance of input path. Dear students, now with the help of example, we'll get inverting amplifier more clear. In this example, you have to find a transfer function V0 of S over Vi of S for the circuit given in the figure. Now if you look at the input path, the input impedance consists of two components, a capacitor and a resistor. Similarly, the feedback path also have two components, a resistor R2 and a capacitor C2. So before solving, we have to find equivalent impedances, and for this we'll replace passive components with their equivalent impedance in Laplace domain. After conversion into Laplace domain, we'll find equivalent impedance. The components present in the input path are in parallel combination, where the components present in the feedback path are in series combination. Now using relations for parallel and series circuits, we'll find the equivalent impedance Z1 of S and Z2 of S. And then we'll substitute these values in our desired transfer function, which is V0 over Vi of S is equal to minus Z2 of S divided by Z1 of S. Students, the second configuration we are going to study is non-inverting operational amplifier. In this case, your output is in phase with input. Now, if you look at the figure of non-inverting operational amplifier, none of the input is grounded directly, as it was in the case of inverting operational amplifiers. And its transfer function is equal to Z1 of S plus Z2 of S whole divided by Z1 of S. Dear students, now we'll study how to find transfer function for a non-inverting operational amplifier. Given we have a figure whose output is V0 of S and the external input Vi of S is applied to second input of operational amplifier. If we look at the feedback path, it starts from V0 of S and it has two impedances Z2 of S and Z1 of S, and then it is grounded. Now V1 of S is a voltage across Z1 of S is applied as a second input to operational amplifier. Now we know that output of operational amplifier is given by gain of operational amplifier A multiplied by the differential input, which is V2 of t minus V1 of t. Now if we apply voltage divider rule in feedback path to find out voltage V1 of S, we will get V1 of S will be equal to Z1 of S divided by impedance of the feedback path, which is Z1 of S plus Z2 of S, and this whole term multiplied by the source voltage. And in this case, loop starts from V0 of S and going through Z2 of S, Z1 of S, and then grounded. So V0 of S act as a voltage source here. So this whole term will be multiplied by V0 of S. Now substituting the value of V1 of S in the difference part of output equation, we obtain a relation of V0 of t, which is equal to gain multiplied by difference of input voltage with V1 of S, which has a predefined relation. Now we will do certain rearrangements to find transfer function when V0 of S over Vi of S. Students, now we have obtained a relation for V0 over Vi of S, but as we know that gain of op-amp is quite high and is ideally equal to infinity. So 1 present in the denominator term is quite negligible compared to the gain of op-amp. So we'll neglect here and we'll obtain our desired transfer function, which is Z1 of S plus Z2 of S over Z1 of S. Students, now we'll discuss an example for non-inverting operational amplifier. In this example, we have to find transfer function V0 of S over Vi of S. The first step in this solution will be transform or replace the passive elements with their impedance in S domain. And then we will use transfer function from last slide. Again, if you look impedance Z1 of S and Z2 of S, Z1 consists of two components connected in a series form, where Z2 of S consists of two components connected in parallel form. So by using desired relations for series and parallel form for impedances, we'll find our desired transfer function, which is V0 of S over Vi of S. And this is all about transfer function for electrical networks. Now we'll start some mechanical systems. Dear students, we have completed transfer function for electrical networks. Now we'll start translational mechanical system and we will study how to find transfer function for them. In this case, we'll again study passive linear components used in translational mechanical system. The first component is a spring, which is the energy storage element. Second one is mass, which is again an energy storage element. And the last one is viscous damper, which is a energy dissipating element. We'll be using these three components in our upcoming topic. Dear students, before starting translational mechanical system analysis, let us study force velocity relation for a spring, viscous damper, and mass. Similarly, force displacement relation for a spring, viscous damper, and mass, and their impedances for spring, damper, and mass. Dear students, now we will study simple translational mechanical systems. To find out transfer function of these systems, we have a few rules to be followed. First of all, we have to define equations of motion. In case of simple translational mechanical system, one equation is required to define the motion of the system. Second step is to draw a free body diagram. In third step, we define direction of motion on free body diagram. After defining the direction of motion, in next step, we will place all the forces acting on the body, either in the direction of motion or opposite to it. And then with the help of Newton's law, we will form a differential equation and sum it to 0. And then using Laplace transform, we will separate the variables and will reach to our desired transfer function. Dear students, now we'll study an example in which we will find a transfer function for a simple translational mechanical system, which is x of s over f of s. To solve this, we'll start from number of equation. As we know that this is a simple translational mechanical system, so a single equation will be required to define its dynamics. In second step, we'll draw a free body diagram. Then we'll define direction and then we'll place all the forces acting on the mass either in the direction of motion or opposite to the direction of motion. Then with the help of Newton's law, we'll find differential equation of the system, and then with the help of Laplace transform, we'll find our desired transfer function. If you look at the free body diagram given in figure A, it states that the object M or mass M is moving towards right, which is the direction of externally applied force. Now we'll place forces acting on the mass M due to components attached to it. The components attached to mass M are a spring and a damper. Now spring will resist its motion and apply a force opposite to the direction of motion, which will be kx of t. Similarly, the viscous damper will also oppose its motion in the direction of x, so it will apply a force opposite to the direction of motion. And lastly, its inertia will also oppose its motion. So these three forces will act in the direction opposite to the x of t, where only force F of t will act in the direction of x of t. The figure P gave us forces acting on the body in Laplace transform form. Now, with the help of Newton's law, we'll find out differential equation of the system. One side of this equation will contain all the forces acting in the direction of motion, which is in this case will be externally applied force F of t, and the second side of equation will contain all the forces acting on the body in opposite direction of motion. So now we'll take Laplace transform with zero initial condition, which will convert our time domain relation into a simple algebraic relation. After taking x of s common from the terms involving it and using cross multiplication property, we'll reach to our desired transfer function, which is x of s over f of s. Students, so now we have found a transfer function for a simple translational mechanical system which consists of a mass m, spring k, and a damper rho v. The externally applied force was F of t, and the system was moving in the direction of externally applied force. In figure B, the very same system is represented in block diagram form, where f of s is input and x of s is the output of the system. Dear students, now we'll study impedance for mechanical system. If you look at the portion of table we studied in the start of translational mechanical system, which gave us force displacement relations for spring, viscous damper, and mass. If we look at the relation for a spring, force is equal to spring constant K multiplied by displacement x of t. And if we take Laplace transform, force F will be equal to K x of s. Now for viscous damper, force is equal to viscous damper constant rho v multiplied by rate of change of linear displacement. Now if we take zero initial condition based Laplace transform, the force will be equal to rho v s x of s. Now for mass m, force is equal to mass m multiplied by double derivative of linear displacement. And for this, in Laplace domain, force will be equal to mass m multiplied by s square multiplied by x of s. Now if we look at force displacement relations for spring, viscous damper and mass, we conclude that force is equal to impedance of the mechanical component multiplied by linear displacement. Or we can say that impedance for mechanical system is force divided by linear displacement. Or we can say that sum of applied forces is equal to linear displacement covered by mechanical component multiplied by sum of impedances. Now if any of you have any questions, please ask.